All right. Hello, everybody. It is March 31st. We made it through another month. And what we are going to do today is two things. One is later on we will start the process of doing a confidence interval when we are looking to see what the differences are between two populations. You still don't have a mic? Okay. Can everybody hear me?
Yes, sir.
Okay. All right. So it's so we're doing okay. All right. The one illustration of this is we're looking at two populations, and we want to know what the difference is. For instance, we want to know how good our third grade reading teacher is. So what we have done is take a random sample of students over the last few years at the end of the semester and measured their reading level. We also went and measured a random sample of students who start her class at the beginning of the semester, right? And figure out what the average reading level is of students that enter her third grade class. And what we're interested in is, on average, how much reading capability does she bring to the table? So for the reading scores, do they go up more than a grade, or how much do they go up? Right? So we need to get that from two different samples, right? And then we're going to ask ourselves, what's the difference between those? In this particular case, we would expect that at the end of the semester, okay, that the students would be doing better than the reading level at the beginning of the semester, right? And that delta is what we are probably going to credit the teacher with in terms of facilitating during the semester. You know, a higher increase in reading levels, grade reading levels, the better the teacher. Not that we would actually give them a promotion for being better, but that's beside the case. Okay. Carlos, you got your hand up. Is there something you wanted to say? No? All right. Okay. Let's keep going then. All right. All right. Carlos, you can't hear me? But everybody else can. All right. All right. All right. I just left Carlos a quick message. All right. Where was I? Oh, okay. We're going to do that at the end of, toward the end of the class, right? But before let's talk about where we are today. We created 4 formulas, okay, for doing confidence intervals. And the confidence interval formulas were these 4. They're on the board. First one, x bar plus or minus z sigma square root of n. Second formula was the identical one, except we replaced sigma with s. We did that because we did not know what sigma was, and our n was large enough that we thought we could get away with it, which in our definition right now is n equals 30. Okay? All right. Next one is x bar plus or minus, instead of a z, a t s square root of n. Okay? And this one is different because we had to replace sigma, which we did not know, with s. But because our n is small, we had a very small sample. We don't have a lot of confidence in our s. Okay? And because of our lack of confidence in s, we ended up needing to go to the t table to get the t value for whatever the confidence level would be. The last class we talked about the special case when we are dealing with proportions. Okay? And in proportions, it is we can take a sample and say, okay, what proportion or what percent of our sample is a success, or whatever we will view as a good thing. What proportion are heads? What proportion are successes? What proportion are equipment that is coming down an assembly line that is in good working order? That type of thing, right? So plus or minus z, and I'm not going to go into small n size type stuff here. Z square root of p1 minus p bar times 1 minus p bar divided by n. Okay. Again, this is formula 1, formula 2, formula 3, and this is formula 4. Now, for those of you who are interested in this, fine. For those who are not interested, okay, just ignore the last second of what I'm about to say, because it's not a real biggie, but it might help some people. I can rewrite this last formula and take that square root. And write it like this. Instead of the square root all the way down, look at that. And then what I basically look at is the square root of p bar 1 minus p bar is the same thing as our estimate of s. Okay. When we deal with binomial distributions, we can kind of figure that out. Okay. But this is kind of how this goes. But instead of having you memorize 4 formulas or one that's not in the book, I am going to stick to these 4 equations, right? Again, in confidence intervals, the first thing is our estimate, our best estimate, which is what we got from the sample, right? And then we put in place the padding, plus or minus how much we have to put on both sides. Okay. Now, usually what we know is we are given n, right? And given our confidence level, we will know what z is or t, because we can look it up in the t table. If we want to do a 95% confidence interval, z is going to be 1.96. We want to do a 90% confidence interval, 90% in the middle, 5% accepting the risk that we're too high, 5% accepting the risk that our interval is too low, right? We end up with a 1.645 z value, right? The t value, we will go to the t table, and for that we will have to know what the degrees of freedom are, and the degrees of freedom are n minus 1, right? And that tells us which row down to go to. And the column will be the column that corresponds to the amount in the tails, each of the 2 tails, right? So we got to this point, right? So we know that x bar comes from our sample, s comes from our sample if we didn't already know what sigma was, right? And then we give the answer to our boss, okay? Our best estimate is x bar or p bar when we're doing proportions, right? Plus or minus z s or sigma square root of n, right? This tells us the padding. And the boss says, but sometimes that padding, okay, is a bit wider than our boss is comfortable with. Okay? We have put so much padding on both sides that we say, boss, we are 95% sure that the number is between 8 and 10. That reality is that mu is between 8 and 10. And the boss looks and says, you know what? That's too wide of a confidence interval. I need something narrower, right? And you say, boss, no problem. I can make it narrower, but what that will mean is you need to accept a lower confidence level. Instead of telling people you're 95% sure, you're going to have to tell them, I'm 90% sure. You're going to have to accept that there's a bigger risk because you have made that padding smaller, right? And your boss says, no, I can't do that. I need a 95% confidence level, but I can't let this be that wide. At this point, you're going to have to talk to your boss and say, boss, we can do whatever you want, but it's going to cost you money. What do I mean by costing the money? Well, I can make that interval smaller because I can make square root of n larger. I would need to make n larger, which means I need to do more experiments. I need to take a bigger sample type of thing, right? I have to interview more people. I have to go into the assembly line and take a bigger sample. All that costs money, right? And the boss will say, well, how much would it cost me, or how much does my sample have to increase if we can make our 95% confidence interval plus or minus 0.5 instead of what you had, which was 0.1. And what the boss is asking for is, how can we make this padding, the plus or the minus, a certain size, right? And so what we can do is take whatever size the boss wants and plug in these numbers, and we create an equation that just looks at this padding, how much we are putting on both sides, make this equal to what the boss is willing to accept, and then we will have to manipulate it so that we can calculate what that n would have to be. If our n were a trillion observations, the square root of a trillion is huge, right? Which means sigma divided by that is going to be very, very, very small. Okay, the larger your n goes, the smaller this whole thing goes. And if you multiply by 1.96, 1.96 times a very, very small number is a very, very small number, right? Okay. So we can do this. And that is how we calculate the sample size we would need to have if your boss tells you, I want a 95% confidence interval, but I don't want that confidence interval to be wider than, let's say, 0.5. So what do? We say this equals, right? And if we do this, there's a 0.5 here, okay? If this is the maximum that your boss is willing to deal with, and your boss wants a 95% confidence interval, We know that Z is 1.96. Okay. Let's say our alpha was 0.25 square root of n. So what we want to do is we are just going to mathematically manipulate this. Okay. So we have 0.5 equals 1.96 times 0.25 divided by square root of n. And n is what we're trying to find out. We're trying to tell our boss how big of a sample do we need to be investigating. Right? So what we want to do is get rid of this on the denominator down on this side and move it over onto this side. So by doing this, we can multiply this side by square root of n. If we do that, we have to do exactly the same thing on this side. Right? This is square root. Right? So what do we have? These here will cancel out. So what we have here is 0.5 times the square root of n equals 1.96 times 0.25. Right? Now we wanted just n. So far, we don't have just n. We have 0.5 times the square root of n. So let's get rid of that 0.5. Again, whatever we do to one side, we have to do to the other, right? In this case, these two things cancel out. And what I'm left with is the square root of n equals 1.96 times 0.25 times 0.5. Okay? Now, we're going to square this in a minute, okay? And because we didn't want to know what the square root of n was, we wanted to know what n was, right? So if we've got the square root of n, what do we have to do to get that square root of n just to be n? Got to square it, right? So if we square this number, okay, we will end up with an n on this side. N equals, but if we squared this side of the equal sign, we have to do the identical thing on this side. So that is still the case, right? So what do we have? Square root of n squared. The square of the square root, these will essentially cancel themselves out. Leaves us with n, right? Equals 1.96 times 0.25, 0.05. And if I take the stuff inside of there, take my calculator so that I can do things properly. Calculator, there we go. Calculator on my phone. All right. 1.96 times 0.25 divided by 0.5 equals 0.98. Squared. Right? This stuff, 1.96 times 0.25 divided by 0.05, okay, gives me 0.98 squared. All right, I hope that's correct. It looks right. Well, what is 0.98 squared? I'm going to my calculator. times, I get 0.9604. And our answer here is a remarkably dumb answer in that as long as we got a sample size of 1, we're okay. Why? Because I had a sigma, which means 0.25, and what was I willing to do? All I wanted was that my estimate is 0.05, 0.5, which is already twice what the sigma was, right? Now let's make this a little bit more realistic. Let's assume the sigma wasn't 0.25, but our sigma was 25. Right? Everything stays the same in terms of the math, except all of these points become 25 using sigma equals 25. I probably should have done this one to start with, right? Well, in that case, what is this equation? Let's do that again. Now, all of the squares and everything still makes sense until we get to this point and we want to fix it. 1.96 times 25. Okay, gives us 49 on top. And on the bottom, 0.5. Okay. It didn't change. Divided by 0.05 equals I get 980. Equals 980 squared. Let me make sure I got that right. 1.96. Okay, I got to clear everything. Here's the clear button. Equal. All right, this is why I'm going to start over because I can't figure out how to clear it. All right. 49 divided by, let me go back, 1.96 times 25 equals 49. Okay. Divided by 0.05 equals 980. Now if I square that number, times 980 gives me n equals 96040. Okay. So in this particular case, we would tell our boss, if you really wanted the plus or minus to be within 0.5, okay, we would need a sample size of 960,400 observations. Almost a million observations. What's your boss going to say? Well, your boss probably is going to say, okay, we don't have that kind of money, right? That's a lot of observations. I'll tell you what, I will be happy with a 90% or an 80% confidence interval because I don't want to spend that money. Oh, by the way, if I'm happy with a 90% confidence interval, what would my N be? Well, you do exactly the same thing, except what would happen? Instead of 1.96 here, you would have a 1.645. Okay, and if that's the case, let's calculate this. 1.645 times 25, okay, divided by 0.05, that's 822, squaring it gives us an N equals 676. Well, what have we done? By being willing to go down to 300, going down to a 90% from a 95% confidence interval, we have reduced our boss's need to do about 300,000 observations. That's a lot of money. Right? Chances are the boss is still going to say, that's still more than 500,000 observations. I can't afford that. Okay. What if I go back here and instead of saying we're going to be within 0.5, if I make this into 1.0? Well, if that's 1.0, then that becomes 1.0. Means this becomes 1.0. This becomes 1. So we don't even need to do that. This becomes 1. This was a 1. And at this point, we had, let's calculate this again, 1.645. I'm all the way down. I've got to turn this off and turn it back on. This calculator. 1.645 times 25 is 41 times squaring that. Equals N equals 1,690. Right? And now your boss says what? Yeah, okay. A little over 1,500 observations. Yeah, let's do it. Let's send out a mail questionnaire so that we get a little over 1,000 responses. If I get 1,000 responses, my N is 1,000. I will know that I'd be able to do, well, I was doing a 90% confidence interval, and I know I won't be off by more than 1. My plus or minus is going to be. All right. So this is how you can use this formula and go backwards to compute the sample size you would need. So the sample size your boss would need to make sure that that padding isn't too big, that padding is acceptable on both sides. All right. Now, if your boss is doing this before you are making any kind of, you've actually gone out to the field, you can do this when you know what sigma is. if you don't know what sigma is, what you need to do is at least get an estimate of what S is, right? So maybe you do a sample of 30 observations just to start with, just to get an S so that you can make this kind of an equation for your boss. Now, if you're looking at a proportion scenario, you do exactly the same thing. You look in the back, right? Okay, and here what you're going to have to do is just get an initial estimate of what it appears that P might be. Okay, the probability might be. Here, a good solution is just go take a small sample, say 20, 30, right? To get a little bit of an estimate of what P bar order of magnitude is. Once you know what P bar is, you know what 1 minus P bar is, and that'll give you an estimate of what you need in order to calculate what the real sample size is going to be. All right. You guys understand? Any questions on what we're doing here? And we can do this pretty much for each one of those. The top one is the most obvious, where you know what the sigma is. Otherwise, you've got to do it with an, with a guesstimate of what sigma is. All right. Okay. So now we are going to go into a different part of the confidence intervals, and this is where we're saying we're talking about the differences, right? Now, in this particular case, we are going to have, in general, 2 estimates, right? Because we have 2 populations. We have the factor in here. I don't know how to build up smoke coming out. Those are supposed to be factories, right? And we are going to want to know something about how much more chocolate does the right Twix plant put in the candy bars than the left Twix plant, right? So what we have here is 2 things of interest. We have reality, which we don't know, which is what we can take a sample, okay, of what the left Twix plant chocolate puts into the candy bar. U2 would be the reality of the second item we're looking at, which is the amount of chocolate that is being put in on the other side, right? So what we want to know, okay, is we want to know something about both of those. And the thing that we're really interested in is mu1 minus mu2. How much more chocolate does the right Twix put in than the left Twix? And you guys all know that the right Twix has more chocolate. Maybe. Okay, but that's what we're trying to estimate, right? We don't know what this is, so we don't know how much this is, how much more chocolate on the right-hand side. Right? We don't know that. We don't know this, and we don't know that. So what are we going to do? We're going to have to take samples. So what are we going to do? We're going to take random samples from the left side, and N1 will be the number of observations we see from the left side. We will take N2 observations from the right side. Right? We are going to temporarily assume that we know what sigma 1 is. We know how much variation there is from candy bar to candy bar on this side, and we will assume we know that on this side. Okay. So we want to make a statement. We want to make a confidence interval statement. We want to say something that says we are at 90% sure, which means we're doing a 90% confidence interval, that what is true? That the amount of chocolate in the right side is this much more. Okay? And so what we end up with is, what is our best estimate of how much more the right is? It's going to be, by the way, forgot one. After we take the sample, we're going to get an X bar on both sides, right? So this is the sample size. This is the average we got. This is the sigma on that side. That. And so our confidence interval is going to be a relatively complicated, long formula, okay? But it's going to look something along the lines of x2 minus x1 bar, right? Why? This is our best estimate of what we wanted to see, right? We will take what we got from the sample of the right-hand side, subtract off what we got from the sample of the left-hand side, and that gives us this difference. And then we're going to add the padding, plus or minus, and then the formula for the padding will become a little bit more complicated. Boy, it's just gotten dark in here. All right, so let me get to the formula. Okay, and we are still in chapter 8, and it is going to be that minus that, plus or minus, again, we will have z, and then instead of just one solution, we will have sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, and this will be the first of our formulas. Okay, in this particular case, we are interested in the difference between these two outputs, mu2 minus mu1. Our best estimate is the difference that we saw from our two samples, plus or minus z, which corresponds to whatever level confidence interval we're interested in, square root of sigma 1 squared over n1 plus sigma 2 squared over n2. But we're going to have different versions of this. If both n1 and n2 are large, in other words, more than 30, our second formula from this is just going to have, we're going to replace this sigma 1 with the S1 that we would have gotten from this sample. We did not know that, we'd have to take it from the sample, and we could do the same thing over here. And then we just go on with life as if nothing happened. All right, we're going to go into this a little bit more detail, one more step as to when this becomes a little bit more complicated, when n's become a little smaller. But we're not going to spend an awful lot of time on it, and we're probably going to finish this up on Monday. Remember, Friday we don't have a class. So I am thinking that the test on everything confidence intervals, I'm looking at a week from Friday. Okay, we'll see how Monday goes. If I finish everything up that I think I will finish up on Monday, then we will have the test on Friday. If I don't get as much done on Monday as I think I'm going to get done, we may push the test back to a week from Monday. All right, and then we will go on to the next thing, which is hypothesis testing. So getting back, it's kind of important that we understand these formulas when you use them. Know when you're reading a problem, what is n? It is the sample size, right? Okay. Of the sample size, what is x bar? What is the average of the sample, right? Okay. What is n? How large is the sample? Do we know what sigma is? Don't we know what sigma is? We don't know what sigma is. We need to use the sample standard deviation as a proxy. Which formula do we use? Right? There are 4 simple formulas, and then there's going to be a couple here that are a little bit more complicated after that. Right? With that, I'm going to call it quits for today. And again, we will probably finish this chapter off on Monday, and then we will go to hypothesis testing after that. For those that, you know, this test you're going to do is going to be very much of know what the right formula is, plug in the right numbers where they belong, and you get the right answer. Historically, students do better in this test and the hypothesis test than they do on the other tests for the year. So hopefully, knock on wood, that will hold true this year as well. Anyways, have a very great holiday weekend. Okay. Remember, Friday we do not have school, so you're free to leave early, go visit your family, and so on and so forth. Be very careful, though, in terms of don't come home or don't come back to campus with COVID, please. And you know, enjoy the little spring break-ish day that we have this year, and we'll see everybody back on Monday. Stay safe and have a great holiday weekend. Bye-bye. Any questions?